Map projections. Previously we noted that the Earth is really big. Not only is it big, but it is a big round spherical shape, called a spheroid. A globe is a very common and very good representation of the three-dimensional, spheroid Earth. One of the problems with globes, however, is that they are not very portable, that is, you cannot fold a globe and put it in your pocket, and their small scale makes them of limited practical use, that is, geographic detail is sacrificed. To overcome these issues, it is necessary to transform the three-dimensional shape of the Earth to a two-dimensional surface, like a flat piece of paper, computer screen, or mobile device display, in order to obtain more useful map forms and map scales. Enter the map projection. Map projections refer to the methods and procedures that are used to transform the spherical three-dimensional Earth into two-dimensional planar surfaces. Specifically, map projections are mathematical formulas that are used to translate latitude and longitude on the surface of the Earth to x and y coordinates on a plane. Since there are an infinite number of ways this translation can be performed, there are an infinite number of map projections. The mathematics behind map projections are beyond the scope of this introductory overview. And for simplicity, the following discussion focuses on describing types of map projections, the distortions inherent to map projections, and the selection of appropriate map projections. To illustrate the concept of a map projection, imagine that we place a light bulb in the center of a translucent globe. On the globe are outlines of the continents and the lines of longitude and latitude, called the graticule. When we turn the light bulb on, the outline of the continents and the graticule will be projected as shadows on the wall, ceiling, or any other nearby surface. This is what is meant by map projection. Within the realm of maps and mapping, there are three surfaces used for map projections, that is, surfaces on which we project the shadows of the graticule. These surfaces are the plane, the cylinder, and the cone. Referring again to the previous example of a light bulb in the center of a globe, note that during the projection process, we can situate each surface in any number of ways. For example, surfaces can be tangential to the globe along the equator or poles, they can pass through or intersect the surface, and they can be oriented at any number of angles. In fact, naming conventions for many map projections include the surface as well as its orientation. For example, as the name suggests, planar projections use the plane, cylindrical projections use cylinders, and conic projections use the cone. For cylindrical projections, the normal or standard aspect refers to when the cylinder is tangential to the equator, that is, the axis of the cylinder is oriented north-south. When the axis of the cylinder is perfectly oriented east-west, the aspect is called transverse, and all other orientations are referred to as oblique. Regardless the orientation, or the surface on which a projection is based, a number of distortions will be introduced that will influence the choice of map projection. When moving from the three-dimensional surface of the Earth to a two-dimensional plane, distortions are not only introduced, but also inevitable. Generally, map projections introduce distortions in distance, angles, and areas. Depending on the purpose of the map, a series of trade-offs will need to be made with respect to such distortions. Map projections that accurately represent distances are referred to as equidistant projections. Note that distances are only correct in one direction, usually running north-south, and are not correct everywhere across the map. Equidistant maps are frequently used for small-scale maps that cover large areas, because they do a good job of preserving the shape of geographic features, such as continents. Maps that represent angles between locations, also referred to as bearings, are called conformal. Conformal map projections are used for navigational purposes due to the importance of maintaining a bearing or heading when traveling great distances. The cost of preserving bearings is that areas tend to be quite distorted in conformal map projections. Though shapes are more or less preserved over small areas, at small scales, areas become wildly distorted. The Mercator projection is an example of a conformal projection and is famous for distorting Greenland. As the name indicates, equal area or equivalent projections preserve the quality of area. Such projections are of particular use when accurate measures or comparisons of geographical distributions are necessary, for example deforestation, wetlands. In an effort to maintain true proportions in the surface of the Earth, features sometimes become compressed or stretched depending on the orientation of the projection. Moreover, such projections distort distances as well as angular relationships. As noted earlier, there are theoretically an infinite number of map projections to choose from. One of the key considerations behind the choice of map projection is to reduce the amount of distortion. The geographical object being mapped and the respective scale at which the map will be constructed are also important factors to think about. For instance, maps of the North and South Poles usually use planar or azimuthal projections, and conical projections are best suited for the middle latitude areas of the Earth. Features that stretch east-west, such as the country of Russia, are represented well with the standard cylindrical projection, while countries oriented north-south, for example Chile, Norway, are better represented using a transverse projection. If a map projection is unknown, sometimes it can be identified by working backward and examining closely the nature and orientation of the graticule, that is, grid of latitude and longitude, as well as the varying degrees of distortion. Clearly, there are trade-offs made with regard to distortion on every map. There are no hard and fast rules as to which distortions are more preferred over others. Therefore, the selection of map projection largely depends on the purpose of the map. Within the scope of GISes, knowing and understanding map projections are critical. For instance, in order to perform an overlay analysis like the one described earlier, all map layers need to be in the same projection. If they are not, geographical features will not be aligned properly, and any analyses performed will be inaccurate and incorrect. Most GISes include functions to assist in the identification of map projections, as well as to transform between projections in order to synchronize spatial data. Despite the capabilities of technology, an awareness of the potential and pitfalls that surround map projections is essential.